Okay, we just talked about vector fields and what a vector field is, and now we're going to talk about vector field operators. So we're going to learn some important general properties, and we're going to see, when we come to physics applications, the connection between a mathematical result and physical properties of the vector field or the system. So I should say, first of all, what is an operator? So an operator is a type of function. So for what we're going to do, we don't need a formal definition. Just think of an operator as something, think of it as a function which takes an input and gives an output. That'll be sufficient for our purposes. So let's learn some vector field operators. First up, swirl. So if you have a two-dimensional vector field, so f of xy equals p comma q, again, remembering that p and q are functions. So in two variables, it is defined like this. The swirl of f equals dq dx minus dp dy. So that's the definition. Let's do a quick calculation. So for this vector field, f equals y comma negative x, let's find the swirl. So notice that q equals negative x, so dq dx is -1. P is y, so dp dy is just 1. So swirl formula, dq dx minus dp dy, -1 minus 1. The swirl of the vector field is -2. Another simple example, this vector field. So vector field f equals 3x comma 2y. Let's find the swirl. So notice that q is 2y, so dq dx is just 0, and p is 3x, so dp dy is just 0. So the swirl of the vector field, 0 minus 0 equals 0. So there's your basic calculation. Now we're going to take a look at the graphs and see what the swirl could actually mean physically. So the first one had a swirl of -2, the second one had a swirl of 0. And here are the graphs of those two vector fields. So check it out. So the reason for the name swirl, I'm going to explain it using the idea of fluid flow. Fluid particles near a point tend to go straight or just spin in circles or some combination of those two things. So the speed of their spinning is determined by the magnitude of the swirl. So the vector field in the first example, you can see at every point there's some kind of circular swirling motion. And we got the swirl with some value was -2. Now, if swirl of a vector field equals 0, the fluid flow is called non-swirling, very straightforward. But look at the vector field, the graph of the second example. That was the one where the swirl equals 0, and you get an idea of what the vector field must look like and what that means. There's no circular movement there. So there's the idea, there's the calculation, and just a quick overview. Note that the swirl operator, what does it do? The input is a two-variable vector field. We're taking the swirl of vector field f, and the output is a scalar. And that scalar we get by taking some derivatives and combining them in some way. So that's the swirl operator. Next, divergence. So divergence of a vector field f is defined as div f equals dp dx plus dq dy plus dr dz. Now I'm giving it here in 3 coordinates, but it turns out divergence can be calculated for a vector field that has any number of variables, 2 variables, 3 variables, 17 variables, whatever. Okay. So now that I've given the basic definition, it turns out that there is a shorthand notation for the divergence formula. And amazingly, it's connected to the gradient. Gradient seems to pop up everywhere. So first of all, recall that the gradient of a function looks like this. We take d dx of f, d dy of f, and d dz of f. I'll work this all out in 3 coordinates. So we could write this down in different notation. We could think of this as d dx, d dy, d dz, all of that applied to f, sort of like the distributive property. And now we could think of that whole, aside from the f, think of everything else as a vector. And that is the gradient operator. So the vector d dx, d dy, d dz is now gradient, not gradient of a function, just gradient, the nabla triangle. So it can be written like this, using either column notation or IJK notation. Now notice that div f can be written as gradient dot vector field f, because d dx, d dy, d dz dot pqr just gives you d dx p plus d dy q plus d dz r. Now, of course, we're being a little bit liberal in our interpretation of what dot means. Now it just means put things together and let them do what they do. Previously, that meant multiplication. But in this case, putting d dx next to p means take d dx of p, for example. So put it all together, and here we have the 2 different formulas, which are definitions of divergence. So to take a step back for a second, notice that the divergence of a vector field can be defined using the dot product. And anything defined with a dot product means the result is going to be a scalar. And also notice that the input is a vector field and the output is a scalar, and that formula involves derivatives of the components. So let's do a calculation to see how it works. So for this vector field, find the divergence. So we say divergence of vector field f equals, so in this case it's 2 coordinates, so it's going to be dp dx plus dq dy, and dp dx is 6xy, and dp dy is just x. So there's your divergence. And again, notice that the result is a scalar. It's a function, but it's a scalar. And then another example in 3 coordinates. So vector field f is xyz I plus x cos yj plus tan x squared plus xy squared k. So let's find the divergence of f on this one. So div f equals dp dx plus dq dy, 3 components, so dr dz. So p is the first component, d dx of that, you just get yz. Q is the second component, which is x cos y, d dy of that, minus x sine y. R is the third component, tan of x squared plus xy cubed. d dz of that, well, there's no z in there, so it's just a constant, plus 0. Just to remind you that we've done it. So there's the divergence. And again, it's a function, but it's a scalar. So that's how we calculate divergence. Again, we can think about what does divergence actually mean for a vector field. So it turns out this. Again, we can think about what it means in the context of fluid flow. So if you have a vector field F, then div F is the net flow of the mass of the fluid at a particular point. So for example, if divergence of F equals 0, then the same amount of fluid always comes in as is going out. And then we say that the fluid and its flow is called incompressible. If the divergence at a particular point is positive, that means more fluid is leaving than is entering. So in a sense, fluid is gained at that point, and that point is called the source. If diversion at a point is negative, that means more fluid is coming in than is going out. So in a sense, fluid is lost at that point, and that point is called a sink. So that's the divergence operator. Next, our third and final operator that we're going to deal with, the curl operator. So what is the curl? So the curl of a vector field in 3 dimensions is defined the following way. Okay. So curl of f, and again, remember that vector field f is just p comma q comma r, where all 3 of those are functions. Here we go. So the first component is dr dy minus dq dz. The second component is dp dz minus dr dx. And the third component is dq dx minus dp dy. And you can write that in ijk notation or in column vector notation. Now, that looks like a lot to memorize. Fortunately for us, there is a shorthand notation for the curl formula using the gradient. Check it out. Turns out that the curl of vector field f can just be written as gradient operator cross the vector field. So it looks like this: d dx, d dy, d dz cross pqr. And if you do your quick curl calculation, you'll see this is just in the first d dy of r minus d dz of q, etc., etc., etc. So personally, I don't even memorize the formula. I just always in my head just take the cross with the gradient operator. Now, something interesting about curl. So first of all, notice that the curl can be defined using a cross product. Therefore, the result is another vector, or in other words, another vector field. And then also notice that for the operator, the input is a 3-variable vector field, and the output must be a 3-variable vector field. And once again, the formula involves derivatives of the components. So now let's do a calculation to see what this looks like. Here we go. Okay. So for this 3-dimensional vector, 3-coordinate vector field, let's calculate the curl. And actually, before I begin, since I'm about to scroll down and show it anyway, there is a definition for curl on the right side here. It can be written in terms of determinants, because cross product can be written in terms of determinants from linear algebra, and therefore so can the curl. Okay, just as a side note. All right, but now let's do this calculation. So curl of the vector field f equals gradient operator cross my vector field f. So what does that give me? So just following the formula, first component is d dy of r. So it's d dy of r is the third component. So 2x plus 3yz minus dq dz. So d dz of x, y, z squared. That's the first component. Next, second component. It's going to be dp dz minus dr dx. So d dz 3xz e to the 2y minus dr dx. So d dx of 2x plus 3yz. There's your second component. Third component, dq dx minus dp dy. So that's d dx of x, y, z squared minus d dy of 3xz e to the 2y. Okay, so there's the setup for the curl. And now just go ahead and calculate all the partials. So that's going to be 3z minus 2xyz in the first component, and then 3x e to the 2y minus 2 for the second component, and then the third component yz squared minus 6xz e to the 2y in the third component. So the curl of our gradient field f is this vector field. Excuse me, the curl of our vector field f is this vector field. Okay. So there is your curl calculation in a standard case. Let's look at two kind of simpler curl calculations for a sec. Suppose we have the vector field f equals yi minus xj plus 1k. Let's calculate the curl for that vector field. So we need dr dy, first component is going to be dr dy minus dq dz. So that's going to be 0 minus 0. And then the second component is going to be dp dz minus dr dx. dp dz is 0, dr dx is 0, so it's just 0 minus 0. And then the third component is going to be dq dx minus dp dy. So q is negative x, d dx of that is negative 1. P is y, d dy of that is 1. So negative 1 minus 1, negative 2. So that just gives you negative 2k. Also, it can be written as 0, 0, 2. That's the curl on that vector field. Let's do another simple, short example. So for this vector field, f equals xi plus yj plus zk, calculate the curl there. So let's check it out. So first component, dr dy minus dq dz. So dy of z, that's 0. And then ddz of y, that's 0. So 0 minus 0 equals 0 in the first component. Second component, dp dz minus dr dx, is also going to be 0 minus 0. And the third component, dq dx minus dp dy, that's ddx of y, which is 0, ddy of x, that's 0, 0 minus 0. So here we just get the 0 vector. So this vector field has the curl is 0. Well, so for these two short curl calculations, I'm going to show you a graph of the two vector fields, and let's see if we can figure out what curl represents visually. So the first one had a curl of negative 2k, the second one had a curl of 0. Let's take a look. Aha. So the reason for the name curl can be understood in the context of fluid flow. So using that language, fluid particles near a particular point, xyz, tend to rotate around the axis determined by the curl vector, and the speed of their rotation is determined by the magnitude of the curl vector. So they do some kind of rotating and also some kind of straight motion or some combination of these two. If the curl of the vector field is 0, that means the fluid is called rotation free. So in the first, on the left, we can see an example of something with the curl in that case was negative 2k. It's easy to see the rotation. It's rotating around the z-axis. I remember that the curl was negative 2k, which points in the direction of the negative z-axis. So there you go. Second one, there's clearly no rotation in the motion. It's just a bunch of straight line motion, and the curl on that one was 0. So curls may seem like a three-dimensional version of swirl, and that's not a coincidence. So for the vector field f equals pqr, make a two-dimensional version by setting r equal to 0. Curl of that vector field is going to be, when you work it out, you'll get 0 in the first component, 0 in the second component. And then in the third component, dq dx minus dp dy. So in other words, you just get swirl of pq times the vector k. So the magnitude of the z component of the curl formula is just the swirl formula. So this can be written in a nice little formula in the following way. If you take the curl of a vector field and then dot it with k, that'll just give you 0, 0, 0 plus 0 plus the third component. In other words, that's just the swirl of PQ. And so for this reason, another name for swirl is the scalar curl. Okay, so let's do a calculation from an application. So electrostatics. That's just a fancy name for charge that is not moving. So we know the formula for the electrostatic force field is this. Vector field F is just KQQ over R cubed times position vector R. So what's the curl? So in this case, to help us out, we're going to write out all the components individually. So remember that the position vector R is just x comma y comma z. So let's write it out like that. And then because we're about to take derivatives, we're going to write the R cubed in the denominator as x squared plus y squared plus z squared all to the -3 halves. So all of that is written out here. Okay. And then also to simplify things, KQQ is just a constant. So we can actually pull that out in front and do all the derivative calculations on just the variables. Let's go ahead and take a look. So doing all the derivatives in the first component, you'll wind up, so the first component, which is dr dy minus dq dz, we get -3yz times, well, using the chain rule. So we get x squared plus y squared plus z squared to the -5 halves. And then doing the derivative here using the chain rule, we'll get plus 3yz times x squared plus y squared plus z squared to -5 halves. Second component, very similar calculation. Third component, similar calculation. I got split up in odd fashion there. Oops. Okay. But then if you simplify in each component, you'll see each one is positive, negative of the exact same expression. So each component is just 0. This is just the 0 vector. So the curl of the electric force field is just 0. But this makes sense because what does the force field, what does the electric force field look like? It looks like this picture on the right. So it all makes sense. And just as a side note, if the charge is not static, the curl is not 0. That's described by Faraday's law, which is a separate thing. But I just wanted to mention that. So far we have met our 3 vector field operators, and now we're going to learn 3 important theorems, which we can think of as facts about or involving our 3 vector field operators, and also in some cases involving the gradient. Let's take a look. So if our function, our 2-variable function f of x, y has continuous second partial derivatives, then we know that the swirl of the gradient of function f equals 0. So let's see what happens there and what that means. So we're going to prove it, and this calculation will be the shortest proof you've ever seen. Swirl of the gradient of f. So the gradient of f we know is just df dx comma df dy. Take the swirl of that. Well, what is the swirl? It's ddx of q minus ddy of p. So that's just fy written in shorthand notation, fyx minus fxy. But we know that as long as second partial derivatives are continuous, you can switch the order of differentiation. So those two things are the same, so the difference is just 0. So there's our first fact. Swirl, so for if a function, for a function of two variables, swirl of the gradient of f equals 0. Now, other ways to say this, you'll recall that terminology we just learned. A vector field f is called conservative when the gradient of some function equals the vector field. So to say this theorem using different terminology, if the vector field f of xy is conservative, then it can be written as a gradient function. Therefore, the swirl of the vector field is 0. So it turns out that as long as the domain is connected, meaning you can make a path between any 2 points, which is usually what we're going to be dealing with, then the converse is also true. In other words, if the swirl of the vector field f equals 0, then the vector field f of xy is conservative. And again, remember that conservative is just the same as saying gradient of some function f equals vector field f. So let us use this to show something. So here's a vector field, and let's show that it's conservative. So if we want a vector field to be conservative, what would show that? We calculate the swirl. So let's go ahead and do it. So swirl of vector field f equals dq dx minus dp dy. So that's ddx of q, which is negative x squared sine y, minus ddy of 2x cosine y. Okay? So what does that work out to be? Negative 2x sine y minus negative 2x sine y. And what do we get? 0. So the swirl of the vector field is 0. Therefore, f is conservative. And again, remember, f is conservative means that the gradient of some function f is our vector field.
Professor, I have a question. What if it's not 0?
Then it is not conservative.
Okay. So we can just justify it's either conservative or not conservative.
By
Nothing
calculating the swirl, exactly.
Okay, thank you.
Yep. Okay, so there is, yeah, so there's our first theorem. That's the first thing that we can check. Okay, so theorem number 2 about our vector field operators. So if we have a function of 3 variables, and again, we need to assume that it's got continuous second partial derivatives, then the curl of the gradient of function f equals 0, or since the curl to the 0 vector. So once again, this is something that we can prove by a direct calculation. Just calculate it. So the curl of the gradient of f is just, remember our short definition of the curl is just gradient operator cross. So it's gradient cross gradient of f. So remember that the gradient of f, of course, is just fx, fy, fz. So now take the cross with the gradient operator, and that winds up giving you f sub zy minus f sub yz in the first component. In the second component, f sub xz minus f sub zx. And the third component, f sub yx minus f sub xy. And in each case, because we know that in this case the derivatives commute, each component is 0, and therefore we just get the 0 vector. And once again, remember that curl is like the three-dimensional version of swirl, and in the third component, we just see what happened with swirl. So once again, using our terminology, we know that a vector field f is conservative precisely when the gradient of some function equals the vector field f. So saying this in different words, vector field f is if vector field f is conservative, then the curl of the vector field equals 0. So what about the converse? So as long as the vector field is defined in all of R3, the converse is also true. So the statement for that is that if the vector field is defined everywhere in R3, and the component functions and everything has continuous partial derivatives, and the curl of f equals 0, then we can say f is a conservative vector field. So the proof of the converse of these statements always winds up being a little harder. And in this case, the proof requires the Kelvin-Stokes theorem, which we will get to in the future. So now let's use these facts. So let's determine if this vector field f is conservative. So notice that this vector field has 3 components. So we check it using the curl. So what do we know? We know that if the curl is 0, then f is conservative. So let's take a look. So let's calculate the curl. Also, for our theorem to be true, we need to check the hypotheses conditions. So vector field f is defined everywhere in R3. Check. All the derivatives are continuous. Check. Because we just have exponential and trig functions and polynomial functions, so everything is fine there. Okay, so now let's calculate. So the curl, so starting off, here is the general formula for curl. And now let's plug it in, evaluate it here. So dr dy, r is e to the z cos x, d of that is just 0, minus dq dz, q is x, d dz of that is just 0. So the first component, 0 minus 0. Next, dp dz minus dr dx. P is y minus e to the z sine x, d dz of that, negative e to the z sine x. R is e to the z cos x, ddx of that is negative e to the z sine x. But we just got the same thing. So subtracted, that's going to give us 0. And then in the third component, dq dx, q is x, ddx of that is 1, and dp dy, p is y minus e to the z sine x, dy of that is just 1. Third component is 1 minus 1, and that's just 0. So the curl is just the 0 vector. Therefore, a vector field f is conservative. Or in other words, there is some function f so that if we take the gradient of it, we get our vector field f. Okay. Now, what I've said is that if a vector field is conservative, it has this function f, which we call the potential function. This suggests a question. What is that function? Let's find it. So as I start this, let me mention there are several ways in which we can figure out what the function f is. I'm giving to you what I think is the most straightforward and easiest to do. So let's take a look. So here's what we know. We know that the gradient of some function must be this vector field. So that means whatever my function is, d dx of that has got to be my first component, which was y minus e to the z sine x. So therefore, if I want to find f, I can just integrate with respect to x. So integrating with respect to x gives me xy plus e to the z cos x. Now, plus a constant. Now, here's the tricky part. I've integrated with respect to x, so my constant is just a constant with respect to x. So if it's constant with respect to x, that means it could include y's and z's. So let's keep that in mind. So the function f had better look like xy plus e to the z cos x plus basically a function of y and z. So now we go into the next component. We know that dy of f had better be my second component of my vector field. So dy of f equals x. So get back to f by integrating with respect to y. So integrating with respect to y just gives me xy, but again, plus a constant. And that constant can include x's and z's. And then in the third component, we know that ddz of f has to equal e to the z cos x from my vector field. So integrate with respect to z, and we get e to the z cos x. But again, plus a constant, where that constant can include, in this case, x and y's. So that's a function of x and y. So now we have to put this all together in make a function such that all three of these things are true. Now, how do we do that? So notice that if you look at the third line, we want the unknown stuff to be a function of x and y. Do we have any terms that are just x's and y's from the previous calculations? Yeah, xy is a term that is just in terms of x and y. So that's probably got to be in there. Next, looking at the second line, the function must be xy plus stuff that is a function of x and z. Do we have a term that is a function of just x and z? Yes, e to the z cos x. So in the second line, probably that's what needs to be there. And then in the first one, the first line, f equals xy plus e to the z cos x plus stuff that's a function of y and z. Do we have stuff that's a function of y and z? Looking elsewhere, no. So zip it all together and all three lines agree. The original function should be xy plus e to the z cos x, and as always, plus some constant c. Okay, so it's very important to pay attention to how these three answers zip together. I think of it as zipping together like a zipper, because not every function needs to have, not every vector field is conservative. Not every vector field has a potential function. So maybe this doesn't work. Let's take a look at another example. Okay, so this vector field is conservative, so let's find its potential function. So I'm already telling you that it's conservative. We could check it, but I'm telling you. So let's find the potential function f. So what do? We know that the first component must be d dx of some function. So fx equals 2xy cubed, so integrate with respect to x. So f has to be x squared y cubed plus something, and that something is constant with respect to x, so it must be a function of y. And in the second component, df dy equals 3 x squared y squared, integrate with respect to y. F had better be x squared y cubed plus something else, so that something else has to be a function of x. So put these two things together, and how do they fit together? Well, in this case, there's nothing to zip together. Everything just matches nicely. And so the potential function is just x squared y cubed plus a constant c. So let's reflect back on this solving process. So sometimes the integrated functions are all the same, like in the second example, and that makes it very easy to state f. But sometimes they're not, which adds a wrinkle to finding f. Now, why does this happen? So if f has terms which do not include a particular variable, for example, z, then when you take a derivative with respect to that variable, that term acts like a constant and will disappear. So it will be missing in one expression, but it'll appear in the other expressions. And that's why you have to do this sort of little bit of detective work and zipping things together. So now we get to our third and final fact about our vector field operators. So if you have a three-dimensional vector field F, so if all the components have continuous second partial derivatives, that's the assumption that we always need for these theorems, then divergence of the curl of the vector field equals 0. So as with with all three of these theorems, we can prove them by just a direct calculation. This one's a little bit longer, but here's how it goes. So divergence of the curl of vector field F. What does that look like? So first we do the curl of F. So curl of F, we just have this formula. It's dr dy minus dq dz, comma dp dz minus dr dx, comma dq dx minus dp dy. Now take the divergence of that. So we know divergence. So divergence, remember, is just ddx of the first component plus ddy of the second component plus ddz of the third component. So it looks like this. So take those derivatives, and what do you get? So using the d notation, you get these 6 different so these are all second derivatives, of course. So you get 6 different ones. But let's look at them. The very first one is the second derivative of r, first with respect to, well, there's dx dy, and then look further down, you get minus second derivative with respect of r dy dx. But again, because they're continuous second partial derivatives, we know that the derivatives commute. So those two are the same thing, so therefore those just cancel. And the exact same thing happens with 3 pairs of second derivatives. There's a minus the derivatives of q were dx dz, and then the other one is second derivative of q dz dx. So all the pairs cancel. And so the divergence just winds up being 0. Okay. So what does this, so this is a nice theorem, a nice fact. How can we use this? So show that this vector field is not the curl of another vector field. So how can we show that? Well, so first of all, using our theorem, we check the conditions. So we need to have continuous second partial derivatives. This is just polynomials and exponential functions. So taking derivatives being continuous, never a problem. So according to the theorem, if G was the curl of F, then its divergence would be the divergence of the curl of F. And by our theorem, that would have to be 0. But what is the divergence of G? Let's calculate it. Divergence of G, ddx of the first component is 2y, ddy of the second component is z, ddz of the third component is x e to the z. Add all of those up to get the divergence. That is clearly not 0. So if it was the curl of a vector field, we would have to get 0, but we didn't get 0. Therefore, it could not have been the curl of another vector field. I will mention just in passing that suppose we calculated that the divergence was 0. Then assuming all conditions hold, then we would know it's the curl of another vector field. Finding the original vector field whose curl is our vector field is actually a fairly complicated procedure that requires some somewhat advanced techniques. But you could find those calculations elsewhere if you wanted. So there's a lot of stuff going on here. So I just want to pull it all together with a summary. So we learned about 3 different vector field operators. So for a 2-dimensional vector field, the swirl of the vector field is dq dx minus dp dy. For any dimensional vector field, here it's written in 3 coordinates. The divergence of the vector field f is just the gradient operator dot f, which in 3 coordinates is dp dx plus dq dy plus dr dz. Then for a 3-dimensional vector field, you can take the curl. Curl of that vector field would then be gradient operator cross vector field. And that formula works out like this. And then under the proper conditions, all these things are true. Swirl of the gradient of the function f equals 0. Curl of the gradient of the function f equals the 0 vector. And then divergence of the curl of 3-dimensional vector field f equals 0. And if we have a situation where the vector field f is the gradient of some function f, then function f is called the potential function of vector field f, and vector field f is called conservative. And then there are some really, really important conservative vector fields: gravitation and electromagnetism. And there are other examples as well. We also went through a process of, once we know a vector field is conservative, how do you find the potential function?